All right, so what do we do today? We start talking about this searching assignment, or do you want to talk about the arrays assignment or something else? Yeah.
Actually, on Tuesday I came in a couple minutes late, and you were going over the some study material for the exam.
Yeah.
Where is that listed?
That's here. There's the recorded video right there.
Oh.
So you can watch that.
But there was also a list of problems.
List of problems?
Yeah, that you said would be similar to what's going to be on the exam.
An exam one from the other course?
Yeah, it's perfect.
Yeah. Let me see. Where did you get that? So you can get to the other course here. There's an exam one link and videos there and notes. These notes aren't too useful, but they just link into the reading material. Let me, so we looked at these. Is that what we did? This?
Yeah, that's what I saw. I just didn't know where it was.
So I'll put it in here. This is the exam one. We did it last time, right? So. Is it, what do I have in this? Do I have arrays? Yeah. Yeah, so maybe I don't need that note. That's a pretty good set of practice problems. So you can get there from there. All right. Yeah, question?
I had a couple of problems with the exercise 3 and the arrays, and Sonia was trying to help me in lab, and she was having a hard time with it too.
This one?
Yeah, and it's exercise 3. The two-dimensional.
Yeah.
Because when she was helping me do the example, she was doing like an inner loop within an outer loop.
Yeah.
And it's kind of confusing the way she was explaining it.
Okay, let's talk about that. So, it's this 2D array here. We did this last time, right? So let's do it again. Here's the example that, here we have an array, a two-dimensional array. It's 3 columns and 4 rows. So 4 rows and then 3 columns. And the problem is to add up all the numbers in there. So I call the function total, create a total of everything in there. So we need to, we can either well, think about how you would do this, okay? How would you do this manually? You could go 3 plus minus 1 plus 0 plus 4. See, I go to the next row, right? And I could do it. I can do it like that. Or I could say, oh, I'll go down the first column. I'll do 3 plus 4 plus 7 plus 0. And then I shift to the next column. See the choice? And you can even do it diagonally too, if you want to go across the diagonals. But so the way I show it is this way, which is you do it, a row at a time. So we're going to do it, add them up, So add numbers, a row at a time. So that means, you know, this came from A00, right? And this -1, that came from A01. The 0 came from A02. And the 4 comes from A10. We have to set the columns back to 0. As we go to the next row, and then we set the columns back to 0. Now we increase the columns again, you know, until we get to the end. And now we're at the last column in row 1. So we got to go to row 2. And then back to column 1. So that's, you know, that's how we do it. So another way to visualize it is see A00, 3 A00s there. So we can just look at it like this. So look here, the zeros are like here. This is column 0, column 1, column 2. So if we use I to represent, or no, use R to represent the row and C to represent the column, you can see you set R to 0. And then you let C be 0. Then leave R at 0. And then increment C to become 1. And then to become 2. And when C hits 3, we've gone too far. That's right here. When C hits 3, we've gone too far. So that means we finished the inner loop. So the changing of C from 0 to 1 to 2, that's done in the inner loop. And when we hit 3, we've gone too far as we exit the inner loop. So when we finish the inner loop, that means this inner loop has completed, it's finished. But that's just one statement in the outer loop. So in the outer loop, we need to, when we finish the substatements in the outer loop, we increment R. So now, you know, R goes from 0 to 1. And then we test the loop condition, which is true if R is 1. And then we do the substatements. Well, the substatement, we only have one substatement, it's for loop. So we have to do this again. Well, we start in all over again. So C is initialized to 0. And we just keep adding it up right here. Does that make sense?
You know how with the one-dimensional you put a closed bracket equals, and then in the parenthesis type symbol you list everything?
Yeah.
Okay. Which one of those is the correct way to list it for two-dimensional?
That's in the main function where you initialize the array. You do it like this, right there. This initializes, well, first of all, there's 12 elements in there, right? 4 times 3 is 12. Well, we don't have to put 12 zeros. We just put 1 0, and the system will add the other 11 zeros for us. That's how you do it. Unless you want to list all the values. So we start with, and here's another way to do it here. Just
so you still just list it in a line?
Just list it in a line. But you do it just the way we did the loop. You know, the line is the first row. So 3 is in column 0, -1 is column 1, 0 is in column 2 of row 0. So you it assigns it just the way we did it in our function. You know, it looks just like that.
So sorry, I'm trying to reiterate. So like when you initialize two brackets,
Yeah.
you have the three. There's the first three are gonna register under the first row, and then the next three are gonna represent the next row.
Exactly. Exactly right. Let's check that, okay? Let's check it. Let's use an assertion. We're going to assert that A of 1, 1, what should that be? Well, this is the 0 row, this is the 1 row. And so 4 is in A10 and 11 is in A11. And so, you know, this A10 should be 4, A11 is 11, and A12 is 1. Did I do that right? Yeah, this is the first row. 3 minus 1, 0 is the first row. So what we're concentrating on is the second row, which is row 1. And the first element in row 1 is 4, and then 11, and then 1. So let's see if we got it right. Looks good. We got it.
In array B, you just put in a single value, so it said 0 for every place value in the array.
Let's check it. Let's check that. Watch this. Let's verify that, okay, just to make sure. We'll just take the second row again. And we want to see that they're all zeros. Okay? All right, let's check that. Looks good. If we left that out, I don't know what we're going to get. It might pass. It does not pass. I got lucky. It's a random memory. Sometimes it's all zeros, but in this case, the uninitialized memory did not contain all zeros. Yeah.
So in array A, you listed all 12 values to fill each place.
That's right.
Array.
That's right.
Let's say you had a third array and you only listed 5 values. What would happen?
Yeah. Okay. That's a very good question. Let's do this. Let's take off these last 3 values. Okay. We don't want the total is not good anymore. So these should hold. And I believe, and it's good to test this because I don't think I ever tested this. It's row 3, that's the last row, isn't it? Because like this is row 0, because we have 4 rows, so that means that 4, we can't use 4 as an index, just the one before it, 3. So our last index in A is, for the rows, is 3. So these, I believe, are zeros. So let's try that. So it sets it to what's called the natural 0. So if it was an array of double, or an array of char, or an array of floats, or an array of long int, those are all numerical values, and they'll all be initialized to zeros. like this. If it's an array of string, it'll initialize it to an empty string. That's a little more complicated. Let's suppose that S is an array of string. I've never done anything like this, so I don't know what's going to happen here. Everything should be empty. In fact, I believe that we don't need that 0. We could just do that. Let's check that. I think that's what we need there. Oh, empty character. That's a string, not a character. Yeah, so we don't even need the 0 here. We just do it like that. So here, we don't need an empty string, but everything will turn out to be empty. So we assert that S of, say, 3, 1 dot size is 0. In other words, it's an empty string. It has size 0. It's a string with 0 characters in it. See, that would be the 0 of the string class. So string is not like a numeric data type. It represents sequences of characters. So if the compiler is going to initialize an instance of string, it's going to set it to sort of the natural 0, which would be a string that's empty, a string with no characters. The string with no characters would have no size, would have size equals 0. Rather. Is that enough? Anything else? Yeah.
For the same one, how would the code be different for if you're using a bool instead of the integer?
A bool instead of an int, like this. Is that what you mean?
Yeah.
So you want to know how that gets initialized?
Yes.
Would it be all false?
Well, it's going to be all false or all true, okay? So let's see. Oh, everybody should take a guess.
Say it's all false. False equals 0, right?
I think it's false?
Yeah.
All false?
And true is 1.
Yeah, that's my reasoning exactly. Yeah. So I say it's a false, and you say it's a false. And no one else is going to gamble today, right? No other gamblers today?
I'll gamble
So, that's false. We got it. Pay up. Everybody else took the other side, right? Okay. All right. So what do you want to do now? Move forward or dwell on this stuff a little more? Forward? Okay. We got to get this done, right? Here it is. So searching. Linear search, binary search, and that's it. 2 kinds of searching we're looking at. So this is good preparation for the exam because we're still going to work with arrays And so here we go. So suppose we have an array of int a of size len, and we need to return, also, we want to find an integer k inside a. So we want to return the position of k in a. So the search function has 3 arguments. As the array a and its length, len, then some number k. And the problem is to find where the first occurrence, I'll just be more precise, the first occurrence of k in a. I'll be even more precise, or -1 if not found. That's what it is. The first occurrence of k in a, or -1 if not found. So we create some sample data first. This is our test-driven development model we're following. Of an array A set equal to 10, -5, 13, 4, -1, 0, 6. That's 7. So we call search with A and its size 7, and let's look for the number 10. That should be in position 0. So when search returns, when we pass these arguments into search, we're asking it to find the first occurrence of 10 in A, return its position. Its position, it's the first element in A, so it should return a position of 0. Up. There we go. So we get lots of test code here. So if we're looking for, -100, that's not in A, so it should return a -1. If we're looking for -5, that's in A, it's in position 1. If we're looking for, we're losing it here, 6.
How do you know what position?
How do I know what position -5 is in?
Yeah.
That's counting it. This is position 0.
Oh,
This is position 1, right here.
then -100
Yeah.
is
What's that?
negative. That's the second row.
Oh, so I got it wrong?
-100 is -1.
Oh, why do we get -1?
Yeah.
Because -100 does not appear in the array. So by convention, what we do is return a -1, because -1 is not a valid position You can't be in -1 position in an array. So this is a convention that that programmers follow. When you want to find something in a list, something that has indices, if it's not in there, then you say it's at position -1. You can't say it's at position 0 because that's the first position. So we just say -1. Now we could have said -2, right? Well, -1 is the biggest, invalid index. So that's a natural choice. So this is a convention that's followed. And 6 is in position, what? Position 6, yeah. Well, that's funny. 6 is in position 6. So that could lead to bugs. So let's change that. Let's make it an 8. 8 is in, that's harder to read. So 8 is in position 6. And then a big number like 999. That should be -1. That's not in there. Look how neat that is. This one's not quite synced up. I can't believe it. I'm wasting time here. All right, does that make sense? So test code. So what's going to happen when we run the program? Should fail. Insertion in line 15 should fail. Because we're returning a 0. It's just a stub called a program stub, function stub. Well, the first one we're testing for a return of 0, so it'll pass through that test, that assertion. But the second assertion in line 15, it'll fail that assertion because the function evaluates to 0 in all cases right now. We didn't do the work yet. I mean, we didn't implement the function yet. So in this line 15, what I have highlighted right there gets replaced by 0. That's what the function returns. So that's what I have highlighted. You can think of it as being replaced by a 0. That 0 becomes the left-hand side of that equality, a comparison operation. So 0 does not equal -1. The assertion, we're passing false to assert, so assert will terminate the program. There it is, line 15, right there. So we got it. We know what we're doing. Now, how do we get this function to return these values, these position values? Well, we need to look for K and A. That means we've got to scan across it. I would start at position 0 and look, is K in position 0? No, okay, is K in position 1? Yeah, oh, okay, it's in position 1, let's return a 1. We don't have to look anymore. You can see there's a loop there. There's an index. The index will say I, and we'll use I, initialize it to 0. It will just we'll look at A of I. You know, if A of I is what we're looking for, then we're done. We can return the index. See, we start with I equaling 0 and we let it go to 1 and a 2 and a 3 like that. And if for any value of those i's that we scan across, if one of them gives us a k, then I is the position of K and A. We're going to turn this into a loop. So we start with I0. Now I needs to be kept less than length. We increment I after each pass through the loop. See that? But there's something missing in there. What's missing in that function? Just a little detail that's missing. Anyone see that? What detail is missing right there? Like -1, right? So if we finish the loop and we never return I, it means we never found K. So we're going to return -1. It's good. That should give it to us. And we get all tests passed. This is called linear search because we're going through the sequence one element at a time. You know, if it takes 1 millisecond to examine one element and increment the index, then it'll take, you know, approximately 1,000 milliseconds to do that in an array of size 1,000. So the amount of work that you do increases proportionately to the size of the sequence. So it's a linear relationship. If it takes, you know, X amount of time to process an array of one element, it'll take approximately, you know, 100 times X amount of time to process an array of 100 elements. So the time required to execute the algorithm is just a multiple of the number of elements in the array. So we call it a linear algorithm. And so we say this is a linear search. But now let's look at something a little different here. Let's suppose I'm going to reorganize these elements. I'm going to put the -5 there. I'll put the -1 here. I'm sorting. Okay, I'm going to put them in sorted order. I'm putting these in order, rearranging the elements. Okay, we put them in order. The test code should, it's going to work a little differently, right? So 10 is going to be in position 5. -100 is still not there, so it's -1. -5 is now position 0. 8 is in position 4. 999 is still not there, it's -1. So we could use linear search for this list, but we can go faster. Imagine, let's suppose that you had these numbers. Let's suppose you had 1 million numbers. We can just do this, no problem, right? We can look at the list. What if you had 1 million integers that were in sorted order, you know, in increasing order, and I asked you to find, you know, 983,619. Tell me if give me the position of that in that list of 1 million numbers. What would you do? Would you look at the first number and then the second number and then the third? No. You'd say, well, let me jump into the middle. And is the number I'm looking for less than that midpoint or higher than the midpoint? Oh, it's higher than the midpoint? Oh, okay, so I'll eliminate the first half of that million long sequence and just focus on the 500,000 numbers that are in the second half. That's still pretty big, 500,000. So I'm going to do the same thing. I'm going to find the midpoint of that 500,000 element long list and say, well, is the number I'm looking for less than or greater than that midpoint? And then I keep having the range until it gets small. And then I find it that way. So that's a lot faster. That's called binary search. Binary means two. So you're cutting something into two. You're taking a big problem and you're cutting it into two pieces. And decide which piece I can discard, which piece that I need to work with, like that. So that's called binary search. Return the position of the first occurrence of k minus 1 if not found. I'm not going to call it first occurrence anymore. I'm going to just say return the first position of k in A. I'm not going to guarantee it's the first occurrence. Just some occurrence. We want to, this is too slow. That's too slow. We don't find it, we'll return minus 1. Yeah, let me leave that out for now. So how do we do this? Well, just the way I said it, we have to have a loop. And in the loop, we keep cutting the range in half. So the range, we need to define the range, we use a start index and an end index. So I'll use S, which will set to 0, and E for the end index, which will be length minus 1. So that defines this range. And then we're going to calculate the midpoint and say, well, is it in the upper half or the lower half? If it's in the upper half, then the start index is going to move it up to the midpoint. So we use a loop. We're not going to use a for loop because a for loop is for a linear operation normally. I mean, you can use while loop and for loops are essentially equivalent, but for loops are typically used to show a linear progression. And a while loop is more generic. So we're going to use a while loop. So we're going to have some condition here to think about. And in this while loop, we're going to calculate the midpoint. Now the midpoint between S and E is just the average. Just take S plus E, divide by 2. That gives you the midpoint. So in our example here, like 0, S is 0. S starts at 0. And E starts at 6. So the midpoint is going to be 3. So the midpoint would be, this would be 0, 1, 2, 3 right there. And it's the exact midpoint because we have a sequence that's an odd number of elements. But if we had an even number of elements, we wouldn't get the exact middle point. We would just be a little shy of the exact middle because the exact, we were looking at integer indices. So we calculate this midpoint and we say, all right, is the value k that we're looking for, is it less than that midpoint? Is it less than the value at the middle index? If it is, if k is less than the value at a of n, that means that k is in the left-hand side split sequence. So we've got to bring E down. Like we're going to bring it down to m minus 1. We don't need to bring E down to m because we compared, so we compared K here. We compared K to 4. I say, well, it's less than 4. K is less than, see 4 here, 4 right there, you see it? That's A of m, okay? And K, in the case that K is less than A of m, that means K is less than 4 in this little example. That means E, we can set E to the position where 0 is here. Because we don't have to look at m. We're going to toss out the first half. We know that K can't be in there, but it can't be 4 either because it's less than 4. So we can toss this out. We know we're eliminating that part of the sequence. So we'll set E to m minus 1. We need the other case. What happens if K is bigger than A at m? If K is bigger than A of m, well, let's suppose K is bigger than 4. Then what do? That means it's got to be in here. It's got to be in there. So one of these, if it's in there at all, it's in that range, right? So that means we've got to bring S up. E is where it needs to be, but S is too small. We got to bring S up to where 8 is there. So we're going to bring S up to m plus 1. Makes sense. You've got m minus 1, then you're going to have m plus 1. Let's suppose that K is neither less than A at m nor greater than A of m. What do? Huh?
Does it equal the midpoint?
Yeah, it equals the midpoint. So we're done. We found it. We found K at m. We'll return m. Good. So there's 3 cases. Either it's less than the value at the midpoint, greater than the value at the midpoint, or equal to the value at the midpoint. If it's equal to the value at the midpoint, we found it at the midpoint m. So we return m. We're supposed to return the position of K, see? We found it. The position of K is A is m. So we're gonna keep making this smaller and smaller all the time. Let's see what happens when it's not in there. Let's do this minus 100. All right. Suppose we're going to execute line 21. Let's look at line 21. We're going to look for minus 100. Maybe minus 100 is okay. Let's look at that one. So we start the algorithm here, and we calculate the S starts at 0, E starts at 6, and M is the midpoint 3. Remember, S, M, and E, those are indices. They're not values. Those are indices. So we compare 4 with minus 100. That means, and then, well, minus 100 is less than 4. So E has to be placed there. So now minus 100, if it's in the array, it's going to be in there. So we start the loop again. We got to compute the midpoint, M. Then we compare minus 100 to minus 1. Minus 100 is less than minus 1. So we set E to m minus 1. That means E is going to sit right on top of S. E and S are the same value now. We got to keep the loop going because we got to look at the value at this E or S. So we compare minus 100 to minus 5. It's not equal. Minus 100 is less than minus 5. Minus 100, K is minus 100, is less than A of M. Because A of M is minus 5. That means we're going to set E to the midpoint minus 1. That means E now gets set to, minus 1. S is 0. So this is the point where we know we don't need to look anymore because we don't have a range anymore. It's not a range of size 1 or larger. Doesn't define a range because E should be greater than or equal to S. So we're done. That's when we finish looking. But we're going to keep looking as long as S is less than or equal to E. We're going to keep looking, and as soon as that relation there fails, then we're done. It could have been that we were moving S up and then S passes E. We could do it like that. So either S will pass E going up or E will pass S going down. That's our loop condition. Well, let's suppose we get to this point where the loop condition fails because we're looking for minus 100. What do we do now? We finished the loop, right? We return minus 1. Yeah. If we finish the loop, because the loop has return m inside. When we find k at m, we return m right there. So we get out of the loop here. But if we never hit this point, it means we never found k. So we terminate the loop and we return minus 1. So let's check. We've got the test code already written. Just got to take out this stuff so it compiles. Search was not declared. Well, I changed the name to binary search. We didn't have to change the name, but just to distinguish our solution, this solution from the last one. All tests passed, we got it. That's binary search. This is a non-linear algorithm. It doesn't go one after another. It's a lot faster. Let's suppose you had 1,024 items in the array. That's 2 to the 10, see? 2 to the 10 power is 1,024. Now see, the range that you're looking at, each time we cut it in half. So in the worst case, when we don't find a value in the array, we're going to cut 1024 in half 10 times till we get to a range of 0 length. So the execution speed of this algorithm is proportional to the log of the array size. It's a lot faster than being proportionate to or proportional to the size of the array. So in linear search, you got to do 10,024 checks for an array of size 1024. But for binary search, you only have to do 10 checks. And it gets, worse. I mean, if it's a billion items, and you got to do a billion checks for linear search, but for binary search, you have to do 20 checks. 20 checks versus a billion, that's a big difference, right? So, binary search is immensely more efficient than linear search. When the size of the array gets large, binary search stays fast. Okay, so that's that. So that's the problem. I showed you how to do this exercise 3. You're returning the position of K and A. But this other problem is to just return true, I found K and A, or false, I didn't find K and A. So that one's not too bad to do. So that means changing this to a bool. See, instead of looking for the position, just tell me if it's there, or false, it's not there. You change the test code like that, right? Then you have to modify the algorithm. Now it's, instead of returning the position of K in A, we've got to return true, I found it, or false, I didn't find it. You can do that, right? Everyone see how to do that? What do you have to change inside there? What do you think?
False return M and return -1.
Yeah, so what do you do? Instead of returning M, what do you return?
Return true.
That's right, good, thank you. And here?
Return
Look how simple that was. Finished. Good observation. And that's it. That's binary search. So this is an easy assignment, this one here, just those 3 problems. Not too bad. Just got to get, it's worth dwelling on this. Spend time with this. Try to figure it out on your own somehow. This is, you'll have to do this later on if you're a computing major. This is an algorithm, so coming up with this algorithm. So that one's pretty easy. Well, not easy. It's not easy, but it's not easy. Not easy, but it's not impossible. So I went to the wrong place. There we go. So that's searching. Now we have 2 more areas to touch on. Vectors. Vectors are very simple. I mean, they're arrays. They're just a different way to work. They're essentially just arrays. So there's nothing difficult conceptually to grasp for vectors. It's just a different kind of syntax. And then classes. This is difficult. This one is hard. So that's it. That's what we have left for the course. Anything you want to do now? We're just finished, right? Take a break? Everyone had enough? Okay, that's it then. Wait, question?
Well, do we have lab? Because I know we have a midterm on Tuesday, but are we having a lab still?
Did Sonia, she said she's going to come, right? Today? Doesn't she normally show up on Thursday?
Tuesday's lab.
Does she come on Thursday?
Yeah, she comes from 12 to 2.
12 to 2, Sonia is normally in the lab. So you can get assistance from her.
Okay, now for the midterm on Tuesday, we're gonna have lab.
We have the midterm on Tuesday, our midterm. Our midterm is on Tuesday, that's right. Does everyone realize that? It's a test? Okay.
Are we gonna have lab after the midterm?
Oh, a lab after the midterm. That was the question?
Yeah.
Sorry, I'm terrible.
That's all right.
Yeah,